In this second video from 8.5, we'll have some example problems using polar equations for conics. In this first question, we have a conic, which obviously a hyperbola. We know the directrix equation, and we know the eccentricity. However, what we do not know are the vertex points. Don't know what those are. Also don't know where the center point is, although I know the center point is over here on this side of the directrix. And the directrix is always between the center and the vertex point. So what we need to do is write an equation for this conic, and we need to find the vertex and focus points in polar form. So that'd be r theta, and I'm using t to stand for theta on this software. All right, so in this problem, because the directrix is crossing the positive y-axis, I know that my equation will take this format. I know my e value, and I know the k value. K is always the distance from the focus to the directrix. So in this case, k is 4. It's always a positive value. So I can just multiply the numerators, and there's my answer. Often in the textbook, what will happen is they don't like the complex fraction element here, so they will multiply by 2 over 2 and rewrite the problem this way. So these are both acceptable. Probably the second one's a little bit better. To find my vertex points are both on the y-axis. For sine, when it's signed, what you'll need to put in is pi over 2 and 3 pi over 2 into your equation, either this one or this one, to get your two answers. In this case here, actually, when I put in pi over 2, I got 12 over 5. And when I put 3 pi over 2, I got negative 12. And so that's a valid answer, but oftentimes the book will like to not deal with the negative. So instead of doing 3 pi over 2 negative 12, they'll rewrite it as an angle of pi over 2 and positive 12. And remember to put the r value first. So I did change it from this to this. For our focus, I know one focus is at the pole. I can see how far it is from that focus to the vertex. I can see that that's a distance of 12/5. And then I just need to duplicate that distance from this vertex to the other to get the other focus. So that would be 12 plus the 12/5. And so that would give me my total distance here. And again, I'm going to use the pi over 2 for my angle there. In the second example problem, it's kind of the opposite of the one we just did. Now we have the sketch, and we know the vertex points. What we don't know is the e or the k value. And can we write a polar equation, or can we as well write the directrix equation for this sketch? Well, before we even start, we know the format of both of these answers. We can see that the directrix will certainly cross the negative x-axis, so we will have a minus and a cosine. And the distance k will be the distance from the focus to the directrix, so it will be x equals minus k. So what I've done is I've taken my equation that I know we're going to have, and I've subbed in our 2 points for r and theta, and gotten a system of equations. Cosine of 0, cosine of pi, I can evaluate. If I cross multiply, both of these equations will equal to ek, so they will equal to each other. So negative 9 times the denominator equals 3 times the denominator, which both equal ek. Then I have a simple equation I can solve for e. I can put it back into either of these equations to solve for k. And then I can replace into the equations that I'd previously set up. I can also sketch my directrix, negative 4.5. Of course, I can find my center point, which is midway between the two vertex points, so I could just find the average of those distances from the focus. And I can see that, yes, my directrix is between the center point and the focus. In this next problem, we are going to take this equation we've been given, and we're going to make a rough sketch of it. And we are also going to convert this equation to general form, standard form, parametric form. General and standard are two different things. Well, the first thing I've done is I've taken my equation and I've divided it through by 5. I need to have that 1 right there. That's what needs to be there in the standard form of a polar equation. Now I can see that my eccentricity is a fraction 3/5, so I know it's an ellipse. I see the minus sign, so I know that the directrix will cross the minus y-axis. Also, I see the sign, so I know that this ellipse is going to go like this, which means I should be plugging in for sine pi over 2 and 3 pi over 2 to get my vertex points. When I plug them in, these are the answers I get. And so I've got my two vertex points. And also my numerator is ek, so I can take my e value and solve for k, so that I then know what my directrix equation is, y equals minus 16 over 3. At this point, I can finish part A of the sketch. I can put my ellipse in here. I can graph my two vertex points that I just found with my r values and theta values. I also know that one focus is at the pole. This is very important because I can find the distance between the focus and the vertex, which is a distance of 2. And so then I can as well make that same distance of 2 in the other vertex focus combination, and that's how I can find my other focus point. I could write it as -6 3 pi over 2. I could also write it as 6 pi over 2, and there's my sketch. To convert to general form, I took my original equation right here, and I cross-multiplied, and so I got 5r minus 3r sine theta equals 16. I remember that r sine theta is equal to y. And I move this term over to the other side, and then I square both sides. The reason I want to square both sides is I want this to be r squared, which is equal to x squared plus y squared. I have to FOIL over here. Then I can bring everything over to one side equal to 0. That's what's called general form. No parentheses, and I just have a string of terms, and that's my general form. Now for my standard form, I could complete the square twice with the general form to get it into standard form, or I could look back at my sketch, figure out what the center point is, because that would be midway between the two focus points, and then I could figure out what A and C are equal to. And remembering the Pythagorean identity for an ellipse, a squared minus c squared is b squared. And I really have all the pieces and parts to write my standard form without completing my square. Now to write my parametric form equations, I just need to remember that cosine squared plus sine squared is equal to 1, or sine squared plus cosine squared is equal to 1. It really doesn't matter which of these you make sine squared and cosine squared. Some like to always make the first one be cosine squared. Some like to be the one with the y be sine squared. The only difference it would make is when the graph is sketched, it might start sketching on the x-axis. It might start sketching on the y-axis, depending on whether you used sine or cosine here or here. We're not really concerned about where it starts and ends. We just want to make a parametric form equation. For instance, in the way that I've done it, you can see that if I put in 0 for t, then x will be 4 and y will be 3. So it will start, well, actually it'll start right here and move from there. But if I had switched the cosine and the sine, so this had been cosine right here, you can see that x would have then been 0 and y would have been 8 when I put in t equals 0. So I would have started right here. But in any event, as I go from 0 to 2 pi, it would have sketched the entire ellipse, or it would have sketched the entire ellipse. One last thing to say about this is that if you wanted your general form, in addition to the way we did it right here, using the r squared is x squared plus y squared, you could have gotten your standard form first with a, b, and c. And once you had this equation here, you could multiply both sides by, what would it be, 400, and 400 would cancel out both of these denominators, and then you could have FOILed out and combined like terms, and you could have gotten your general equation. So It's up to you whether you get the general equation by cross-multiplying the original or by getting your standard first and then foiling and multiplying out to get rid of the parentheses. In our last example question that we're going to do, we have a standard form conic in polar form and with no numbers in there, and we're going to rotate it 70 degrees counterclockwise, and after we do that we want the equation of the new conic, the new directrix, and the new focal axis. To rotate the conic, that's the easiest one of all. We just have to put minus 70 degrees when we want to rotate it in this direction counterclockwise. If we rotated it clockwise, we would have to write plus 70 degrees. Remember, it's in the parentheses, so we do the opposite of what you would expect if you do a positive 70-degree angle, minus 70. As far as the directrix goes, we know that it's a minus and a cosine, so we know that the original directrix would be x equals minus k. Of course, x is r cosine theta in polar language, and then we could solve for r and get the original directrix in polar form. And now we could as well put the minus 70 degrees with the theta to have a polar of our rotated directrix. Of course, we could go back to what we knew did in 8.4, where we would write our line in parametric form, x equals minus k and y equals t, and we could use cosine, cosine, minus sine, sine of 70 degrees. Now that would be a positive 70 degrees that we would use here, cosine of 70 minus sine of 70. And we could do the matrix multiplication, and we could get an answer in parametric form for our new directrix. For part C, our original focal axis is y equals 0, and we are going to rotate 70 degrees, and so our new focal axis will be like this. And now that's just a line passing through the origin. So y equals mx plus b, the b is 0, and the m is the tangent. So that would be the rise over the run, that would be opposite over adjacent. So this would be a nice rectangular form equation for our new focal axis. We could be slick about it and write a polar form equation. Maybe remember that theta equals a number would say this line at 70 degrees, theta equals 70 degrees. Or, if you want to really be mathy, you could make one of the letters in the rectangular be equal to t, either one in this case because it's linear. I picked x to be t. And then y would equal tangent 70t, and you would have parametric solution, or polar, or a rectangular solution for the new focal axis when it is rotated 70 degrees counterclockwise.